Hello, welcome to Mickey Techie. Learn as engineer, teach as champion. First of all, I would like to thank my family for their continuous support and encouragement of creating these kinds of technical videos in public domain. And I would like to thank my mentor, Professor R. Surendran from Government College of Technology, Coimbatore, for igniting me a spark of creating these kinds of technical videos in public domain. I would like to thank Almighty my God for my good health and broad mind, and I would like to thank my friends, followers, my dear students, and subscribers for continuously watching my videos. Today's topic of interest is entropy. We know that entropy is the outcome of a second law of thermodynamics and it deals with quality of heat content or quality of heat transfer takes place in a system, that is called entropy. And we know that the entropy change in entropy of the universe is always increasing in manner. So with this short notes, I would like to give a short and quick summary about the entropy in second law of thermodynamics, that is entropy in heat engine, heat pump, and refrigerator. We are going to discuss in a very short summary. Here I would like to go with the entropy and classes and Joule Thomson coefficient for the entropy purpose. Here the heat engine, we know that heat supplied is more than heat rejection. Here QA is the heat supplied, and QR is the heat rejected. We know that the heat engine, heat pump, refrigerator, all are the devices which having two heats. One is heat supplied and another one is heat rejected. So with these two conditions we are going to play. Here in the heat engine, work done is equal to heat supplied minus heat rejection. Therefore the efficiency is equal to work done by heat supplied. We know that work done by heat supplied is the efficiency, where work done is the QS minus QR or QA minus QR. Okay, and if it is a reversible heat engine, the efficiency of the heat engine becomes T1 minus T2 whole divided by T1. T1 minus T2 whole divided by T1. And next, it is a heat pump, where in the heat pump, heat rejection is more than heat supplied. Heat rejection is more than heat supplied, whereas the work done is equal to heat rejected minus heat supplied, and it gives a heating effect. What is meant by heat pump? It will give a heating effect. So QR is a heating effect, where here we mention COP instead of efficiency. COP means coefficient of performance. Coefficient of performance is heat rejected divided by work done. Heat rejected by work done. We can say, if you compare the COP and the efficiency, efficiency is work done by heat supplied. Here heat rejected by work done. That means the efficiency and COP are inversely proportionals. So the efficiency is equal to 1 by COP. With this information, this thing you have to be know. Efficiency is equal to 1 by COP. Therefore, efficiency of the heat engine into COP of heat pump is equal to 1, which is equal to 1. So this you have to notice this. Okay, so this is the important relation, that COP of heat pump into efficiency of heat engine, which is equal to 1. You can compare here. Okay, from heat engine to heat pump. Therefore COP is equal to heat rejected divided by work done, that is QR divided by QR minus QS. If it is a reversible heat pump, COP is equal to T1 divided by T1 minus T2. The refrigerator and heat pump are the same to same. that is QR is more than QA, where heat pump does the heating effect, where refrigerator does the cooling effect. The work done, they have a same formula QR minus QA, whereas COP, it is heat supplied by work done. Here it is heat rejected by work done in heat pump, heat rejected by work done. Here it is heat supplied by work done. So this is the difference between the heat pump and the refrigerator, where COP is equal to QA divided by QR minus QA, where if it is a reversible refrigerator, the COP is equal to T2 divided by T1 minus T2. The relation you have to notice this is, you have to do a notice a COP of heat pump minus COP of refrigerator is equal to 1, and similarly COP of heat pump into efficiency of heat engine is equal to 1. So these two relationship you have to notice this. Next is a Joule-Thomson coefficient. Joule-Thomson coefficient, that is mu is equal to dou T by dou P at constant enthalpy. So this we have to remember by try play hard. Try play hard. Like that you can remember this formula. And similarly the Clausius-Capron equation. Clausius-Capron equation is significant in phase change process. We know that in the phase change process the device used is either a evaporator or a condenser. Condenser we can use the Clausius-Capron equations, where we are discussed about only latent heat, only the latent heat. So this information you have to notice this. And Clausius-Capron equation is the dP by dt is equal to del H enthalpy divided by temperature into the specific volume difference. So this we can notice this. Try please try HTV. So please try HTV. By this we can easily remember the formula of Clausius-Capron equation. Next, the entropy, we know that it is the quality of heat content, where this Clapeyron equation ds is equal to q by dq by t. So that we have to know. If this is equal, so ds is equal to dq by t, then it is a reversible process, where cyclic integral of del s or ds by dt is equal to 0. And similarly, if it is the ds is greater than dq by t, then it is irreversible. Therefore cyclic integral of ds by dt is greater than 0, sorry, it is less than 0. And ds by ds is less than dq by t, that it is impossible. So this relation is impossible, whereas this relation is possible. Here this relation, change in entropy is constant, it will say. It change in entropy is increasing, it will say. And here the change in entropy is decreasing. Here it is not at all possible that the universe, the change in entropy of the universe is not at all decreasing, either it will be constant or increasing in manner. So that is why this equation is not valid, not at all valid, where the above two equations are valid. So it is impossible to make ds, that is change in entropy, is less than dq by t. So cyclic integral of ds by dt is greater than 0, it is not at all possible. Then entropy, in the entropy of the expansion process it is decreasing, entropy of the compression process is increasing, heat addition it is increasing, heat rejection it is decreasing. Here we can know that the heat and the entropy are directly proportionals. If heat increases, entropy increases. The expansion process, change in entropy in the expansion process, it is negative, and the compression process it is positive. Heat addition it is positive, heat rejection it is negative. So with this condition we can know the relation between the heat and the entropy. Whenever the heat is increased, the entropy is increased. Next, TDS relation. TDS, that is nothing but dq. dq is equal to TDS. This is the relation found from this equation. So ds is equal to dq by t. So it is an for reversible process. So it is for reversible. If the process is reversible and non-flow, therefore TDS is equal to du plus PdV, where if it is a flow process, TDS is equal to dH minus VdP. And next, if we coupled two reversible engines, there is a two conditions. One is if it is having equal efficiency or it is having equal work done. If it is having equal efficiency, then the intermittent temperature T2 is equal to T1 into T3. When if it is a work done, the intermittent temperature is equal to T1 plus T3 whole divided by 2. So with this, the summary of the entropy is being completed. So with this, I'm going to close today's session. If you have any doubts, please let me know in the comment section and I will put another video for clarifying your doubts. So thank you for patient listening. Thank you once again. Bye bye from Santhosh. Thank you.